All right, everybody, this is the first of 3 videos for our very short Unit 5, and the only standard in this unit is this one here. Describe key graphical characteristics of different functions and to perform function operations. So our first video is going to focus on the first part of the standard, and that's identifying different functions and their characteristics. Make sure you write down what we're studying, and then go ahead and we'll get going. All right, so we're going to be starting with just a list of different names of functions, their parent function, what they look like as an equation, and then a sketch. And you should have a worksheet that I handed out, so this should be all organized for you, and you can just write everything on there. There's just so many different graphs, I wanted you to have them on paper. All right, so here we go. The first one is linear, and we should know what this one looks like. It was in one of our first units. So our linear standard, our linear standard, our linear function is f of x equals x. Okay, and what does a sketch of that look like? A sketch of the parent function goes right through the origin because I didn't put any transformations. I didn't translate it up or left or right. I didn't put any stretches, which is like a slope. So this is our parent function of a line. The next one's a quadratic, and that's the unit we just recently finished. So this is f of x equals x squared. That's the most basic squared function we have, and we get a little parabola out of that with its vertex at the origin, and it's opening up because we did not move it left, right, we didn't move it up or down, and we did not put a stretch on it. The square root function actually looks kind of like half of our quadratic, because remember, if quadratic is squaring something, square root should be related. So this is what our square root function looks like as an equation. It is simply the square root of x. Now, in a square root function, we're only using real numbers. We're never going to be dealing with imaginaries because we don't know how to plot those imaginary points, and they need to be plotted on a special coordinate plane. It's not the real plane with x's and y's. So we will only work with real numbers. So x has to be, in this case, greater than or equal to 0. It's a must. So that's our domain, actually. And the way it starts is it starts here at the origin just like our x squared did, but it becomes half a parabola. The reason it is not the bottom half of the parabola is because, first of all, that would make it not a function. Think about if I drew the bottom half of this parabola. It would not be a function. So we have this part right here. And we're going to talk more about these functions. This is kind of like just get the names so we understand what they're called. The next one's called a cubic. And a cubic function just means that we take x cubed. And a cubic function looks really cool because it's kind of like a parabola on this side that opens that way from the origin, but on the other side it's like a completely different parabola. Now, it doesn't have a parabolic shape in the sense that it's not x squared. So it does grow much more rapidly because you're cubing numbers. And the reason it goes down is because when you cube negative numbers, so let's say I cube -1, it's a -1, not a +1. And when you cube -2, it's a -8. So that's why it goes down on the one side but up on the other. The cube root, similar to the square root function, is kind of sideways. Now this is going to look interesting because you've not seen this before, but I put a little 3. It's not a big giant 3 like a multiplier outside. It's actually a different symbol. It's called the cube root, and that's just the cube root of x. And so the cube root of x function does kind of look like a parabola on the side this way and a half a parabola that way. So this is the cube. I'm going to highlight it for you. This is the cubic, and the second one over here is the cube root. Okay, keep going. All right, so the next two, one of them should look familiar to you, and that is the absolute value function. And the most basic absolute value looks like this, with its vertex at the origin, and it's a v. The next one is called a step function or a greatest integer function. And our step function looks like a basic, it's kind of a piecewise function, Well, it is a piecewise function, but not all piecewise functions are step functions. Step functions literally look like steps, but they're floating steps. So let me explain. You're not going to connect the steps together, because if I connected them with vertical lines, then it would not be a function, because the vertical line is not a function. So they're literally just little steps like this. And they could go the other direction. They could come down this way, like so they would look sideways like that. I'll get rid of that. So these are like a little step function. Now, the greatest integer function, and this is something we need to be able to recognize, it looks like there's absolute value bars, but they're kind of these extra bracket things, and this is called the greatest integer function. And it looks just like a step function, but it's got a specific pattern that it follows, and we can discuss that more when we're in person. All right, so now we're going to be talking about continuous functions and determining whether or not functions are continuous. And continuous means exactly what you might think it means. It means it does not stop. It does not have breaks. So a continuous function, you never lift your pencil up to get to the next spot. It goes on forever. It is continuous. It has a left, a right, and it goes on forever in the x direction. So this first one is an example of a square root function. So that's a square root function, for example. And I can say that this is not continuous because it has this end point. So this is not continuous. The next one is an example of, it's actually an example, it says floor up here, that's what you're seeing, and a floor function is like a greatest integer function, and it's these little steps. And notice how there's an open circle on one end and a closed circle on the other of each of these little steps. And as you can imagine that I am skipping, my pen is moving up and down and up and down, I'm not keeping it on the screen, so this is not continuous. Let's go to example 3 over here. So this is our third example. And once again, I do have something that looks like a piecewise function, but this is not continuous because I have to pick up my pencil to get to the next. All right, this last one here is an example of a cubic. It doesn't start at the origin. It's been shifted. This one's been stretched, actually. And it's actually, I was going to say, has it been, no, it's not flipped. It's just stretched. And what we can see here, though, if there were arrows, which there are intended to be, that I never have to lift up my pencil, that I can go to infinity forever in both directions with not lifting up my pencil. So this is continuous. Woohoo! All right, the next thing we're going to talk about is domain and range. And this is a little bit of a review. You can find domain and range regardless of whether or not this is a function. Because you see, this is a function because all of my x's are different. And here, this particular x value has 2 y values. So this is not a function. But that does not mean that we cannot find the domain and range. So my domain and range are based on, are there any stopping points? So this is an example of, I'm going to say it's an x to the 4th graph. I'm not certain, I'd have to do some calculations, but we're going to call it an x to the 4th graph. So it's a little bit different than a cubic, but it kind of has an interesting shape like a W. And what I can see is there's this bottom spot right here, what we call like a minimum. And so I would say that my range, talking about my y values, go from -6 up towards infinity. But my x's, well, they're going to continue to grow out, and these are going to continue to grow to the right. So my domain in this case is all real numbers. Now on this circle graph that we have here, I have a high point, I have a low point, I have a left, and I have a right. So this is giving me my domain and range. I'm kind of boxing this circle in. And I would say my domain, being all of the x values, goes from -1 to +5. And my range goes from -3 up to +3. Let's talk about the next one here, this sideways absolute value. This is not a function because this x value has two y values, so this is not a function. But we can still determine the domain and range. So my domain are all of the x values, and I see that my smallest x value, kind of like a minimum but sideways, is 1, and it goes to infinity. It goes all the way this way. We can keep going with all of those. And then my range values, well, these y's are going to keep growing and they're going to keep falling down. So in this case, my y values are all real numbers. This one I love because it's a step function and the domain of it actually has to be listed. It has to be listed because I'm talking about all of the values between 1. Actually, my domain doesn't have to be listed because I'm including from, what is this, 1, 2, 3, 4. So -4 up to -3, but I am including -3, and then up to -2, but I am including -2. So my domain actually is all real numbers. But my range, because I'm skipping the y values and I'm just using integers for my y values, I would have to list them. So it looks like this. Dot, 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 -3, comma, -2, comma, -1, comma, 0, comma, 1, comma, 2, dot, dot, dot. Now, what does that show? It shows that I'm using just the integers, but I want to use the positives and the negatives. So I have to show a variety of them so that the person reading this knows that I want all of those numbers, but I'm specifically talking about integers. You could also write a sentence. It could be the set of all integers. So you could write the words, the set of all integers. All right, moving on from domain and range, the last thing we're going to talk about is increasing and decreasing. And increasing and decreasing intervals. So these are going to be written in interval notation, just like your domain and range. My increasing and decreasing values, increasing is when you can see a positive slope, and decreasing is when you see a negative slope. And I am using the word slope very loosely. I'm not talking about a slope of a line necessarily. I'm talking about, is this increasing over time? As in, is it getting higher? And we are always moving from left to right, like you're reading a book. So if I were to look from here to here, is it going up? Yes, it's increasing. So on what interval is this increasing? Well, it starts increasing at 0. You're like, no, it's up at 3. No, the x values are doing the increasing. From 0 up to infinity, this will continue to increase. The next one. On this one, you can see that they're rising over here, and then they're falling, and then they're rising. So this one actually has 2 intervals of increasing and 1 interval of decreasing. So from here to here, in other words, on the x-axis, from here to here, so I think that's -6. I wrote too much on the picture, I can't even see it anymore. So we would say that the interval of increase, well, it's actually negative infinity up to -2. Okay, so all of this is increasing. It's all going up. So from negative infinity to -2, we're increasing. And then we start increasing again when we get to +2 to positive infinity. This is all increasing. So we're gonna get a chance to talk about this in class, but please take notes. I know this might be a little bit challenging to do on the paper. But we'll keep talking about it. So this interval in between here, which happens to be from -2 to +2, that's your decreasing interval. These first two are your increasing intervals. So this is our last graph, and we're going to talk about it. So we're going, I can see right here around -5 is where the decreasing stops. And it goes from negative infinity to -5 because I'm talking about the x values in which this is decreasing. So from negative infinity to -5. Then it starts to increase in this little interval right here, which means from -5 to -2, I see an increase. Then I see it decreasing again. It decreases, sorry, this keeps clicking. It decreases from -2 to +2, that's decreasing, and then it starts increasing all the way up to infinity. So from +2 to infinity, it is increasing. All right, so you've got your worksheet. Hopefully you've got this all written down. I want you to look back at it and think about where is the lines going up and where are the lines going down. Where is it falling? Where is it rising? And that's your intervals of increase and decrease.